Travelling to distant stars might sound like science fiction, but perhaps it's not as outlandish as it seems. This episode, I'm speaking to NASA scientist Les Johnson about the possibility of interstellar travel.
My name is Les Johnson. I'm a physicist, and author of popular science and science fiction novels. And I also work at NASA, where I'm a space propulsion technologist. I've been there about 30 years. I have to give a caveat whenever I mention my NASA affiliation. I don't write books as a part of my day job, and anything I say is my own opinion, not that of my employer.
Cool. Well, yeah, thanks for coming on the podcast, Les. It's really, really good to have you on.
Well, thanks for having me. I look forward to the discussion.
Yeah. Now, the reason our paths have crossed is because of your latest book, which is A Traveler's Guide to the Stars, which is a scientific look at interstellar travel and venturing beyond our solar system, which is obviously pretty exciting. Sort of sounds a bit like science fiction. But I was hoping to come to sort of start off by going all the way back, because at the start of the book you say this all started for you when you led NASA's Interstellar Propulsion Research Project in 1999. And I was wondering if we could go back to that moment and what was that group all about, and why do you sort of pinpoint that as such a life-changing moment?
Well, you can tell I've been at NASA for a while. The lack of hair kind of betrays that. It really goes a lot further than that. That was a pivotal moment in my career, but my love of interstellar travel goes back to being a child, watching Star Trek, reading every science fiction novel I could get my hands on as a student, both in undergraduate, graduate school. Today, I still am an avid reader of science fiction, and I love thinking about what the human species can do in the future with regard to traveling to the stars. And it was a real pivotal moment for me, because I went to work for NASA knowing I'd be working on space technology and different space aspects. And up until 1999, which I'd been there for about 9 years at that point, I'd been working on different propulsion technologies, totally unrelated to what might take us to the stars. And I was in a meeting, a newly formed group called the Advanced Space Transportation Program, right? Great name. And I was the youngest person in that group. These were many, many veterans of the technology programs that had developed, like the main engines for the space shuttle, right? Some of the people in the group, mostly men at the time, had even worked on Apollo or Skylab and were close to retirement. So this was a very venerated, experienced group of people in propulsion, but they were all rocket scientists. And what I mean by that is chemical rockets were everything to them, right? Whether it be liquid, solid, whatever. And when they thought advanced propulsion, they were thinking of incremental increases in the capability of chemical rockets. I was working at advanced propulsion technology that something called an electrodynamic tether, a totally different divergent topic, but it's a way to move around in space with a long wire with a current flowing through it, and it lets you maneuver in magnetic fields. But that's why they brought me in the group, because I had a flight experiment that was getting ready to fly, and it certainly is an advanced propulsion thing. Well, at the time, the NASA administrator, Dan Golden was his name, wanted to challenge NASA to do a mission farther than we've ever done before, not to another star, but to something to succeed Voyagers. The Voyager spacecraft had been launched in 1977 on their way out of the solar system. And he said, I want to send a mission that can go 10 times farther than Voyager is going to be able to go, that travels 3 times faster. He gave the job to NASA's Jet Propulsion Laboratory, the Deep Space Mission folks, and said, put a team together to do this. Well, where I work at the Marshall Space Flight Center, it is the center for propulsion, mostly rocket propulsion, but propulsion in general. And they asked for someone to come out and spend weeks with this JPL team as the propulsion lead, trying to figure out, how do you do that? How do we do something better than Voyager? So they asked for volunteers, and I heard a bunch of these people all groan and mumble about how impossible this job would be. Why would anybody want to think about that? Because obviously we don't have the technology today to do it, because they were all chemical rocket types. And they thought, this will just be a study that goes on a shelf and nobody does anything with the results. Well, I had been in the group for a few weeks, and I'm looking around at all these experienced engineers that I just revered, all basically trying not to look at the manager, afraid they'd get tapped and have to go to JPL. So I thought, well, why not? So I raised my hand, and it changed my career. It was wonderful. I went to JPL. I was with people thinking about exotic far out kinds of things. I learned about the real state of the art of advanced propulsion that's not chemical rockets, nuclear propulsion, electric propulsion, solar sails, other things. And shortly thereafter, I came up with a plan of what we needed to do to see if these technologies could be advanced to the point where we could use them. And the next thing I knew, I got a budget and I stood up the Interstellar Propulsion Technology Project, which ran for a couple of years and then morphed into a more general space propulsion technology project that was very well funded. And we made a lot of progress. So I think we're taking those first steps to enabling that mission we were asked to go look at in 99 across the agency. And I'm doing my little part with some of the technologies that I'm working on. But for me, it was all about raising my hand. It was like, ask Mikey, the young guy. Nobody wants to do it. I'll do it. They all looked relieved. And I went to JPL and had a career and life-changing experience.
Incredible. I mean, I suppose when you consider that was the late 90s, the sort of the context of that was we'd only just confirmed exoplanets. Was that part of the discussion? Was that part of what you and NASA were thinking of at the time?
It was not. That's too far away. I think it was exciting, and people thought, well, eventually we might do that. But right now, how do we do better than Voyager? And just to give you an example, today in late 2022, the Voyager spacecraft are at about 150 to 160 astronomical units, which is 150 or so times the Earth to Sun distance. And they've been flying for 40 plus years to get there. And this team was tasked with getting something that could fly 3 times faster to cover that same distance in a third the time, right? And even doing that is not anywhere close to going to the stars, but it would be a huge increase in capability of what we can do today. So yeah, the exoplanet stuff was intellectually interesting. People like me who've been reading about life on other planets, Star Trek, Captain Kirk, Picard, they're all visiting these other worlds, right? To me, it was like, oh, okay, well, of course we're going to do that someday, but how do we take those first steps? And that's what really got me fired up.
Yeah, it is really interesting also because I sort of think that when you look at Apollo and then the shuttle and then what we're doing with with the Artemis missions and the potential of going to Mars, have we really changed? Has propulsion in that respect really changed very much since Soyuz and the Apollo in a sense that we're sort of launching rockets to go to the moon or into Earth orbit? Has it really changed since the days of those first Soyuz launches and the Saturn V?
We have to break that into 2 parts. The first part is getting off the Earth. There's a certain type of propulsion you need to get out of the Earth's gravity well. I mean, we're stuck here. It takes a lot of energy to get off the ground and get into space, and rockets are really hard to beat for getting out of the Earth's gravity well and into space. So the first 400 miles. We've been using rockets since, I guess, as Von Braun was building V2s in the 40s, right? All the way up till today. And the innovations that we see from the commercial rocket companies that have revolutionized the cost model are still basically chemical rockets, right? I don't think that's going to change anytime soon. I think we will be using chemical rockets to get off the ground. What will change more, and has already changed, is how we get beyond that first 400 miles or 400 kilometers, give or take, right? It's 1,000 miles, 1,000 kilometers, just out of the Earth's gravity well, right? A long distance. Because the spacecraft then have to go the next million or billion. And when you think about that, the power of a chemical rocket doesn't look as good because it's extremely inefficient. If you put it in terms of your car, the miles per gallon of a rocket is poor. Its efficiency is very, very poor. There are other methods to move around in space where you get 10 times as much total velocity change for the same amount of propellant or the same amount of mass. Things like electric propulsion, ion drives. Those have been flown in space since the late 90s and are used on commercial satellites in Earth orbit, like the big communication satellites. They're used for station keeping. We've sent missions to asteroids. The Dawn mission went to the main belt asteroids using electric propulsion after a chemical rocket launched it. I'm working on solar sail technology, as are others. And I believe we're soon going to be again flying nuclear rockets powered by fission rocket engines, which will be fantastic for opening up the mid-solar system, Mars and Jupiter, both for robotic missions as well as human missions. So if you break it into those two parts, you're correct. Getting off the ground really hasn't changed, but we've made a lot of progress, not enough, but a lot of moving around in space once we get off the ground.
So if you were asked just that flat question, is interstellar travel possible? Is it currently possible, given what we have and what we know, to get a spacecraft from Earth to a different star, like a different solar system, a different planet orbiting a different star?
Well, you're talking to someone who has to split nuances here. The answer is yes. The Voyager spacecraft, if they were pointed in the right direction, will be dead and non-functional, but they could arrive at another star system in about 70,000 years on their current trajectory. So technically, yes, we can send a probe to another star. Is it practical? Absolutely not. I don't think anybody would say a 70,000 year mission of a dead spacecraft is practical. From the point of view of fundamental physics, there are ways we can accelerate spacecraft much faster and reduce that trip time to 1,000 years in some cases, which isn't as outlandish as most people might think, because we have recorded history going back 1,000 years, to a few hundred years or less, which is even better, because to listeners in Europe in particular, not so much North America, you have projects that took hundreds of years to complete. The great cathedrals, right? Those were multi-generational lifetime projects. So I think within the known laws of physics, we could undertake a voyage that could get to another star in a few hundred years. And if some of the technologies pan out, which we don't know that they will, maybe in 100 years. But I have to point out there's a difference between physics and engineering. The fundamental physics says these approaches might work, and I talk about those in my book. But if I turn around and talk to the engineering teams that I work with and say, okay, go build this, well, in their mind, they're probably laughing at me. But in reality, they're thinking, we don't know where to begin because we don't have the engineering skills to build spacecraft to travel these distances that fast today. But if you look at the fundamentals, all the way down to Newton and quantum mechanics and everything else, we ought to be able to figure it out. Okay. We just haven't committed the engineering time and talent to do that yet.
I really love that analogy. I'd never thought about that before. You know, the great cathedrals of Europe, whose architects never saw them being completed. Because when you think about traveling to our nearest star system, you sort of think, well, that's not possible within one human lifetime, and you sort of your instinct is, well, that's pointless then. But it's not pointless, is it? I mean, as you say, even great engineering works. Maybe in like 200, 300 years time, if we have mastered it, people look back and go, oh, but back then, the people who launched the spacecrafts didn't even see them arrive at the distant star system.
I think it enables us, well, it requires us to take the long view. And I think that's something woefully short in global society today. Everything is investments, technologies, everything we do is couched in near-term return on investment. Can you bring money back or accomplish this in 3 years or less? And I think we're losing a lot because some of the greatest things we've done in human history have taken far longer than that. And I don't think we ought to undertake things that we believe are impossible over multi-generations. But if you have a good plan and it's worth doing and it takes longer than my lifetime, and I won't be here to see it completed, I think I would take great satisfaction in knowing I was a part of it at its beginning. And that's the way I think about things. I think that's a mistake we often make in our society is we don't take the long view. I think we need to look forward and realize that some things are worth doing, even if you or I personally won't see them to their completion. And the notion of sending our presence, the human species, life as we know it, into the universe beyond just where it arose or was created here is vitally a moral imperative to me. And I think you can make that case that life is good and we ought to do this. So that long view is just really missing, and we should get it back in every aspect of our lives.
It sort of brings up a vision or like a scenario where if if human beings were to travel to a different star system, then the people who launched from Earth wouldn't be the people who arrived. It'd be their grandchildren. Do you, which itself, I mean, there's bound to be scientific or sort of sci-fi novels and films that have been written about that, that sort of idea. Do you think of that as a possibility?
Well, I have to parse the problem. It's going to be hard enough just to send a robotic probe the size of the Voyager spacecraft. In fact, the energy required to get that going at something like 10% the speed of light would give a pineapple, if we launched it across interstellar space, the same energy equivalent as like 7 nuclear bombs that were dropped on Hiroshima. And that would just be from the energy of motion of accelerating a pineapple to 10% the speed of light. So I think we first have to think about how we're going to send a robotic probe that will send back pictures and scientific data from a close flyby of some of these extrasolar planets before we ever start thinking about sending people. Sending people will require spacecraft that are much, much larger, because basically we're pretty massive, and the things that are required to keep us alive on a voyage like this would be a lot of weight. And to accelerate that to these speeds would be a lot harder. So I tend to separate things into, if you can think of it as a nearer term, if 100 to 300 years is nearer term, that'll be a robotic spacecraft. And after we do the robotic exploration, then I think we can think about sending people. And that'll be a much slower trip. And then you get into all kinds of ethical questions, right? About future generations aboard the ship that didn't sign up for where they're going. And is the destination going to be habitable? Probably not. We're probably not going to find another Earth out there like in science fiction, where you can just, go down to the planet and breathe and eat and walk around. That's very unlikely. It's more likely we'll find things like Mars, Venus, Europa. And then you have the question of, well, what do you do with people when you get there? Do you terraform the planet to make it suitable for life if it's dead? Or what if you get there and there's already life? Then I don't think you should do anything. I don't think we should interfere. We should have our own prime directive kind of thing. So the issue of sending people gets problematic. I think we'll eventually do it, but I view that as a much longer term project than sending the robotic probe.
I love the point you make in the book, where it would take so long for a robotic probe to get there. And then there's obviously the issue of power, keeping it alive. So do you hibernate it until it gets there? And then you've got to somehow justify to the taxpayer, this is going to take 100 years, but we're only going to get 2 hours worth of data.
Well, that's right, because unless you can slow down, which makes the problem twice as hard, at least, by the way, you're moving really fast, which means when you get to the exoplanet system, you're going to fly through that whole solar system in hours or days, right? So your data is going to be very quickly received and transmitted back, and then you're back out in deep space again. So I think the way this will become practical is if we find a way to launch many probes inexpensively to many different destinations, so that when our descendants are listening or looking for the data, depending on radio or optical communications or however the data comes back, they don't just get data from, Proxima Centauri b. They get it from a whole host of exoplanets, and they get a rich data set of what's out there. So this really can't be a one-off, in my opinion, or a two-off like the Voyagers. We need to think about how to launch a lot of these probes in a cost-affordable way to get them going really fast, to make that, I hate to use the term, but I'll use it anyway, the return on investment, right? The science return, to make it worthwhile with that long term.
What about the potential data that you would collect on the way? Is that possible? In other words, I suppose, is there a way of keeping it powered as it's getting there, and without having to make it sleep and not be collecting any data until it gets there?
Yes, physics says that's possible. Absolutely. In fact, you could take the technology we have now in nuclear power plants here on the Earth, where you fission uranium, and you could make a small reactor that could keep a spacecraft alive at low power for a 100-year voyage. I don't think people know how to build that today, but I think most engineers that work in the nuclear industry, if you gave them the challenge and some money, this is a thing that we could probably solve in 10 or 15, maybe 20 years. They think they could come up with an engineering concept that would work for that. Now, it might be heavier than my pineapple. I mean, it might end up, weighing something like a Voyager 1,000 kilograms or a few thousand kilograms. But I think they could miniaturize a reactor to do that. There might be better ways to do it with some of the advanced technologies that are out there, but that's one we could probably tackle in the nearer term, is the power.
Is this an opportunity to talk about your work on solar sails? That's something I'm really interested in, and yeah, I was wondering if you give us a bit of a background as to what that is and what your work is and how that comes into the picture of interstellar travel.
Sure. Let me tell you why I like the idea of a sail of some kind, and that is because you don't carry the propulsion with you. You don't carry fuel. All of the fuel is off board. And what that means is you don't have to accelerate the weight of all that fuel as you are moving, right? So if you can find a way to get the energy from somewhere else to accelerate your spacecraft, it makes your spacecraft lighter and easier to accelerate. And that's why I like sails. So if you think about a solar sail or its cousin, a laser sail, so I'll just maybe use the term a light sail. The way it works is this. I can see you on screen. People in your home can see you. And that's because light reflects from you and goes to their eyes. Light's made up of these little particles called photons. Photons, they don't have rest mass, but they do have momentum, which means like a BB being shot at a sheet you hang up, when the little BB hits it, the sheet recoils a little bit. That push can make the sheet move if there's no resistance to its movement, which in space there isn't. There's no air, get away from the gravity, the sun's always shining. So if you have a large, lightweight reflective material, and I'm going to hold up a sample of solar sail material here. This is the actual material from which we're making solar sails today. It's about the thickness of a human hair. It's made of plastic. It's a polyimide, and it's coated with aluminum. This piece is kind of wrinkled because 1,000 people have held it, but it's pretty robust. You see, it's got a tear, so I could tear it in two, but if you just handle it, you're not going to damage it. Yeah. And it works the same way as a sail that people are familiar with. If they go to the ocean or a lake and they see people windsurfing or sailing, they put up the sail, and on Earth, it's wind reflecting from the sail that pushes it. In space, it's light. And it's a very small push, but it's constant. The acceleration accelerates you constantly. So when you put out a large lightweight sail, think something that's 1,000 square meters up to 10,000 square meters, and in my imagination, a square kilometer, right? And you deploy it very close to the sun where the sunlight's very, very bright. You get a lot more light on the sail. It will accelerate it to very high speeds. And so a square kilometer sail deployed within a few solar radii could accelerate a small spacecraft so fast that it might be able to go to the nearest star in 1,000 years, say, or give or take, depending on the characteristics of the sail. That's a long time. You can make it go faster if you build big high-energy lasers, deploy them in space, and I'm not talking about puny 10-kilowatt lasers that the DoD is building for their ships, right? 30 or 50 kilowatts. I'm talking about gigawatts, billions of watts. And you shine these lasers on this sail as it's exiting the solar system, then you can get trip times of less than 100 years to the nearest star. So I am a huge advocate of something other than a rocket. No matter how efficient a rocket is, you still have to carry all that fuel, and that's a problem. If you can take that energy off board, you can go faster. Now, solar sails, not laser sails, have been demonstrated. NASA flew one called NanoSail D in 2010. The Japanese flew one called Icaros in 2010. The Planetary Society's flown one. NASA just launched the Near-Earth Asteroid Scout to demonstrate a sail. And my team at work, and again, I'm just telling you what NASA's doing. You can find this on the internet, so I'm not giving away anything inside. We're working on one that would be 1,600 square meters, which is over 17,000 square feet for American listeners. And that's huge. And it gives you a capability to do science for scientists today that they don't have. But my dream is that this is the first step to that square kilometer sail and then the laser sail, and that my great-grandchildren will use the technology that I'm working on today and send that first probe.
So cool. I love the idea of it, sort of like a boat with a sail, but rather than wind, it's light. There's something kind of quite poetic about that, isn't there?
Oh, it's beautiful. It's elegant. In fact, I've talked to a lot of audiences about this. It's kind of the ultimate green propellant, right?
Yeah.
And it has a I don't know. I think it appeals to the romantic notion of sailing. I mean, sailing's always appealed to people, right? And I think it just kind of touches us in a way that's not just technological. It touches us in a kind of a romantic way as well. At least that's the way I look at it.
Definitely. Are there any sort of at least proposed techniques that are a bit more outlandish? And I'm sort of thinking about, the stuff that they really do explore in science fiction, like, you know, bending space-time itself in order to travel instantaneously through space faster than light. Is that something people like you sort of genuinely are interested in and genuinely consider potentially a possibility as we do things like discover gravitational waves and photograph light warp bending around a black hole and the warping of space-time?
Okay, this is where I have to be really careful. Within what we know about physics today, December 2022, we do not believe it is possible to warp space-time and bend space-time to go to the tremendous speeds that you hear about with some of these theories. They are fantastic physics models, but you can build a mathematical model predicting how the universe works. And nature doesn't actually work that way, even though the math is good, right? And I love this kind of theoretical work by people. For instance, the warping of space-time, the Alcubierre drive that Miguel Alcubierre came up with. There are people seriously looking at this, but there are a lot of theoreticians. And no offense to my theoretical physics colleagues, that's not really meaning to demean you in any way, because you're doing the necessary kind of thought experiments that might lead to a physical breakthrough to enable us to do these things. But almost all of them require us to have some form of matter that we don't know that it really exists. For example, negative mass. I have no idea what that is, right? But it turns out in some of the mathematics, if you change the acceleration due to gravity, which is positive, to a negative, lo and behold, you can bend space-time. No one's ever seen negative mass, so we don't know if it exists or not. So I would put that in the speculative physics category, in that it seems physics-based, but it's speculation, okay? And that's great. We ought to pursue that. These theories are how revolutions happen. Einstein's general theory of relativity was a theoretical construct until they validated it by experiment and observation, right? So I'm hoping that some of these really neat ideas, wormholes, bending space-time, that look like they might be possible if we make a certain discovery, let's hope we make that discovery, because it'll make the job of going to the stars a heck of a lot easier. But right now, I'd put it in the speculation category. I wouldn't put it in the I'm going to bet my retirement savings that will make it work category.
We've talked quite a bit about how we get there and all those different forms of propulsion and all the different techniques and engineering and physics. But I suppose it is also worth talking about destinations. Like, when you think about interstellar travel, do you have an end destination in mind, or do you just think how do we get to the nearest star, or is there anything beyond that? I'm just interested in what sort of destinations you and your interstellar travel colleagues might have in mind.
Well, I think the first low-hanging fruit that you want to do is the nearest star and the planets around it, because obviously it's closer, even though the distance is immense, to try to do that. But I think ultimately we want to survey, the 100 nearest star systems that have planets before we decide to take that step to send people on a voyage. You have to send them somewhere where there's a hope for survival. And that might take some looking, and it might take far more than the nearest 100 systems. So I think our robotic exploration phase will be an extended phase. Again, though, one thing I don't want to underestimate is the pace of technological change in areas outside of, quote, interstellar travel technologies. We're in the century of biotechnology. As the 20th century was the century of physics, the 21st century is the century of biotechnology. Who knows what those great-grandchildren of mine will look like, how long they'll live, how disease-resistant they'll be, what their lives will be like. Who knows in terms of creating food and the laboratory, what environmental support systems might look like in 150 years. So I think we can't discount the fact that that these voyages with people might look very different than we envision them today. But I'm kind of limited by my blinders of, people as we know them today going, we're going to need data from hundreds of star systems before we find one that might be suitable for us to live on. But then again, maybe we find an environment that instead of modifying the environment for us, our descendants modify themselves for the environment. And that opens up a whole other, can of worms in terms of possibilities. But it's fun to think about, and we shouldn't underestimate what those changes might be in the next several hundred years.
Yeah, absolutely. I mean, I remember, I think it was about a year ago, I was talking with Emily Lakdawala, the planetary scientist Emily Lakdawala, and she was talking about, even for something like exploring Venus, those like suits where you're in Earth, but you're controlling a suit. So there's a robot effectively representing you on Venus, and you can survive you can effectively walk around on Venus through virtual reality. So, something like that might be quite cool as well for exoplanet exploration.
The time delay would kill it.
Yeah.
Unless we have an instantaneous communication network. It's 4.5 years of light speed travel time. So, you take a step and you wait, 9 years to take the next one. So, but yeah, you're right. I think the virtual experience might be something they do initially, and they might do it initially from the spacecraft that's orbiting the planet, right? Establishing the base might be done by these telerobotic operators from orbit, where they're experiencing the planet vicariously until it's ready for them to go down and move into their habitat or otherwise. So yeah, I agree. Those changes are coming. And we don't know what the impact from all that will be. A lot of creative people out there will take it in directions you and I can't imagine.
Yeah, and I suppose that is another issue as well, isn't it? If you were to send humans to Alpha Centauri, for example, the time delay in sending them a message and getting the message back, as you say, would be so long that it would it would almost render it. It's just sort of almost pointless attempting to even have a conversation with them, wouldn't it?
It would. I think anyone we send is going to be on their own.
Yeah.
And they'll be able to get periodic data from Earth, latest technologies, latest news, family news, etc. But whatever they do, it'll be years out of date. And the thought of a two-way conversation will just be pretty much impossible within what we know about how nature works today. Now, there are a lot of people working on some pretty cool things like this quantum entanglement. Spooky action is at a distance that Einstein called it. It's my understanding you really can't use that very well to transmit information, but there are a lot of creative people trying to find ways around that I actually associate with and have interesting lunchtime conversations with. But who knows? I think a lot of those things will appear and change the way we look at how you ultimately do the trip.
Yeah. I mean, as we're recording, it's we're sort of approaching the end of 2022. So yeah, I was just going to get your final thoughts. Just sort of what are you hoping from the field in 2023, or indeed your own work? What are you sort of most looking forward to over the next 12 months?
Well, I think the first thing I'd like to do is invite your listeners to consider attending the 8th Interstellar Symposium, which will be held at McGill University in Montreal next July. I think it's July. It's a week-long symposium of scientists, engineers, science fiction authors, artists, general public who will be presenting papers and discussions talking about the ethics and the technologies of interstellar travel. And those meetings have historically resulted in innovative new technology papers and thoughts that get published in a peer-reviewed journal, Acta Astronautica, which is a pretty big prestigious journal in the aerospace community. So I would encourage anyone who's interested to consider attending that and joining us in Montreal next summer, first and foremost for 2023. And in 23, I'd like to see the work continue on a lot of these advanced propulsion technologies for certain. In the work I'm doing on solar sails, I want to press forward with that. I think also the field I mentioned earlier of nuclear propulsion, there are investments being made around the world in trying to further that capability. And I think as we look at going to the stars, we'll have to take the solar system as a stepping stone to get to the stars. And so anything that's going to get us further into space and get us more used to working and living and operating beyond Earth is a step to the stars. And so that's another thing I'm optimistic that we'll see happen in 2023 and beyond, is that we'll take those next steps toward flying some of these advanced technologies.
Fantastic. Yeah, lots to look forward to in this field alone, when you consider everything else that's going on. But yeah, Les, just want to say thanks for coming on the podcast and for speaking to us. And good luck with the book when it comes out around about the time of this podcast, Traveler's Guide to the Stars. And yeah, hope to get you on the podcast again soon, maybe, and we can talk about any new developments. But yeah, thanks again for coming on.
Well, thanks for having me. It's been a fun conversation.